It is a very hot day in the Triassic, the first period of the age of the dinosaurs. An animal called Ephygia eats plants in a forest lost in time. At first glance, it looks like a dinosaur with a long neck, strong hind legs, and an upright posture, but it actually isn't one. It belongs to a group of reptiles more closely related to crocodiles than to dinosaurs. Meanwhile, in the shallow waters of the Triassic seas swims Henotus, a shell-bearing reptile that looks like a turtle, but is not a turtle either. It is a different kind of reptile called a placodont. It is as if nature were making trial versions of animals that feel familiar to us, but using completely different body plans. Almost anywhere in the Triassic we could find animals that remind us of creatures from later, better-known eras, but that in reality belong to different families with their own evolutionary history unique to that time. The Triassic fauna is probably the weirdest, most unusual and strange that has ever existed on Earth. The huge variety of new animal forms that appeared then can only be compared to the Cambrian explosion, which took place 300 million years earlier. Since that moment, never again did so many different animals evolve in such a short time, not even after the asteroid that wiped out the dinosaurs, except for those that gave rise to birds and allowed the beginning of the age of mammals 66 million years ago. The Triassic was a gigantic evolutionary laboratory on a planetary scale. But why did this happen? What was so special about the Triassic? How did it begin? And how did it end? Why do its animals seem so strange to us? To answer these questions, in the first part of this video, we'll look at the history of the Triassic and the beginning of the age of the dinosaurs. In the second part, I'll introduce 15 little-known animals from that time, which will reveal important things about the history of life and paleontology. Spoiler, none of them is a dinosaur. And in the end, we'll use all this to try to answer the big question. What was Mother Nature doing at the dawn of the age of the dinosaurs? This is the story of the Triassic explosion. To understand the story of the Triassic, we first have to look a bit further back and see what the world was like before. The previous period is called the Permian. It began about 298 million years ago and ended 252 million years ago, right when the Triassic started, which lasted around 46 million years. That was plenty of time for several revolutions to take place in the life of the planet. Over those millions of years, entire continents collided, mountains rose, and oceans disappeared. At the beginning of the Permian, the world was colder and had more oxygen than in the Triassic due to an ice age called the Karoo glaciation. Tetrapods, animals with a backbone and 4 limbs, were adapting to life on land because the climate had become drier after the collapse of the great tropical rainforests. Their carboniferous ancestors had displaced the arthropods, such as insects and their relatives, as the main land animals. Little by little, vertebrates began to occupy nearly all the planet's ecological niches, setting the stage for the radical changes that would come with the end of the Permian and the beginning of the Triassic. During the Permian, many different types of amniotes appeared. These were tetrapods adapted to life on land thanks to a special kind of egg. Before them, tetrapods were more like amphibians, tied to water like modern frogs. The amniotic egg, protected by a shell and with internal membranes that keep the embryo, food, and waste separated, allowed these animals to reproduce away from water and occupy many new environments. Thanks to this portable incubator, they were able to colonize deserts, dry plains, and regions far from rivers and lakes, which made it possible for them to diversify enormously. The first amniotes to become really varied and successful were the synapsids, the group from which, many tens of millions of years later, mammals would emerge. However, true mammals did not appear until the end of the Triassic. In other words, the Permian synapsids were not mammals. They were ancient branches of that group that split off before the common ancestor of all modern mammals, and almost none of them left descendants. Even so, they were the unquestioned stars of their time. For much of the Permian, synapsids dominated most terrestrial ecosystems, occupying the roles of predators, herbivores, and scavengers. Some of these proto-mammals developed huge, barrel-shaped bodies with small heads, capable of eating large amounts of plants. One example is Caudelorhynchus, one of the largest caseid synapsids. It must have had a very strange appearance. A heavy, bulky body, sturdy legs, and a relatively tiny skull, as if someone had mixed the proportions of several different animals. It is possible that one of these caseids had a semi-aquatic lifestyle, similar to that of modern hippos, resting in shallow water to better support its weight and feeding on soft vegetation. This shows how diverse this group was in the early Permian and how, long before the dinosaurs, nature was already experimenting with gigantic forms and a wide range of ways of life. Over time, many of these synapsid lineages disappeared, swept away by extreme climate changes and, later, by the Great Extinction at the end of the Permian. But they left behind key anatomical innovations: differentiated teeth, more upright postures, changes in the skull, that would be inherited and refined by their distant descendants, the mammals. In a sense, every time we see a cow, a dog, or ourselves, we are seeing the modern version of a story that began with those strange, heavy synapsids that walked through the dry landscapes of the Permian. At the same time, other carnivorous synapsids appeared that would later dominate ecosystems. The pelycosaurs, such as the famous Dimetrodon, known for the large sail on its back. Although it is often mistaken for a dinosaur, it lived about 50 million years before the first dinosaurs appeared. It probably used its sail to regulate its body temperature, warming up quickly in the morning and losing heat at dusk. Some scientists have also suggested that it could have served for display, to attract mates or intimidate rivals. Its jaw already showed an early division between different types of teeth: incisors, canines, and primitive molars, the beginning of more efficient chewing and a way of feeding more similar to that of modern mammals. In the last millions of years of the Permian, synapsids gave rise to more advanced forms, the therapsids. Some, such as the dinocephalians and gorgonopsians, reached enormous sizes and became the planet's top predators, with impressive fangs and powerful skulls. Others, like the dicynodonts, were large herbivores with horny beaks and robust bodies, capable of processing large quantities of tough vegetation. The world was full of them. On almost any continent, it would have been easier to run into a therapsid than any other kind of large animal. Before the age of the dinosaurs, this was, in reality, the age of the proto-mammals. However, the Permian was about to end with the greatest biological tragedy in history. 252 million years ago, this period ended with the largest mass extinction known. Around 96% of marine species and 70% of terrestrial species disappeared. Ecosystems collapsed almost completely. Not even the asteroid that wiped out most dinosaurs caused such extreme damage. For millions of years, huge volcanic eruptions in Siberia released gigantic amounts of carbon dioxide and methane into the atmosphere. Global temperatures rose, the oceans became acidified and stagnant, oxygen levels fell sharply, and food chains collapsed one after another. It was literally hell on Earth. Poisoned seas, skies full of ash, and continents scorched by unbearable heat. When that crisis finally ended, the planet was almost empty. And yet, in that emptiness, an opportunity also opened up. A new world waiting to be recolonized. The perfect setting for the strange evolutionary explosion of the Triassic that would begin shortly after. The soil became dry and poor, Acid rain destroyed entire forests, and deserts spread across the continents. Animals that depended on abundant vegetation died, and then the carnivores that depended on them fell as well. In the oceans, the lack of oxygen allowed bacteria that produced hydrogen sulfide, a poisonous gas, to proliferate, contaminating both water and air. In short, the entire planet became toxic to life. To a modern observer, it would have been an almost alien landscape. Murky skies, dull, lifeless seas, and continents covered in reddish, eroded ground with hardly a trace of green. At the start of the Triassic, Earth was a desolate place. In the interiors of the continents, daytime temperatures could exceed 50 degrees Celsius, while the poles were almost mild. In many areas, there was hardly any vegetation, and only a few tough species survived. Among them were the dicynodonts, herbivorous therapsids with robust bodies and horny beaks, and the cynodonts, small carnivores or insectivores that would be the distant ancestors of mammals. The latter, about the size of a small dog or even a large mouse, lived in burrows, using the shade and humidity underground to escape the extreme heat. Early Triassic times were an era of pure survival. Ecosystems were very simple and fragile. The planet was trying to rebuild itself from scratch. Rivers and lakes carried a lot of sediments and sulfur compounds, and the seas were still recovering from the chemical collapse. For millions of years, the world remained unstable. But little by little, life began to reorganize. Some pioneer plants, resistant to drought and poor soils, started to cover certain areas, stabilizing the ground and creating small oases where other organisms could take advantage of shade and moisture. From these minimal nuclei, ecosystems began to become complex again. At that time, Earth was dominated by a single supercontinent called Pangaea, an enormous block of land surrounded by a single global ocean, Panthalassa. In the interior of Pangaea, the climate was very hot and dry, while the coastal regions were more humid with monsoon-like rains. This huge, continuous landmass allowed many animals to move and spread from one end of the planet to the other. A single group of reptiles could extend across thousands of kilometers, which meant that many Triassic faunas were surprisingly similar, even if they lived in regions that today are very far apart. Then, the first truly modern reptiles began to diversify. Among them were the archosaurs, the group from which crocodiles, pterosaurs, and dinosaurs would later arise. But at this point, they were still small animals, adapted to survive the harsh conditions of the early Triassic. Their light bodies, more upright limbs, and possibly more active metabolism gave them an advantage over heavier, slower reptiles still adapted to the Permian world. The giant amphibians that had survived the Permian also continued to exist in swampy areas. Some, such as Geronthorax, had flat bodies and wide heads and could remain motionless for hours, hiding underwater to ambush their prey, much like crocodiles do today. Others, like Benthosuchus, were more active and hunted fish in the murky rivers of this new world. They were living reminders of an older Earth, creatures that seemed pulled from prehistoric nightmares, clinging to their last aquatic refuges while, little by little, reptiles and future dinosaurs prepared to take over life on land. Little by little, the landscapes began to change. The volcanoes that had previously caused so much destruction were now enriching the soils with minerals. The same eruptions that had contributed to the Permian collapse became a source of nutrients. Ash, rich in phosphorus, potassium, and other elements, fell to the ground and made it more fertile. New plants colonized the dry lands: hardy ferns, horsetails, cycads, and the first conifers. These forests were still low and sparse compared to modern jungles, but they were enough to start transforming the landscape. The atmosphere, although still loaded with carbon dioxide, began to stabilize, which allowed vegetation to flourish again. Over time, herbivorous animals expanded once more. Dicynodonts thrived on the plains, feeding on these new plants. Some grew as big as an ox, like Cannemyria, which probably moved in herds, grazing among those primitive forests. Carnivorous cynodonts, meanwhile, became the top predators of the early Triassic. They were small, agile, and had different types of teeth, a first hint of what mammals would later become. They probably hunted at night or at dawn, using their keen sense of smell and perhaps a higher metabolism than other reptiles. Life was starting over. The mass extinction had erased almost everything that came before, but that emptiness left a lot of free space in ecosystems. And when nature has space, it fills it with new forms of life. From very simple communities, a few herbivores, some predators, and pioneer plants, more complex food webs began to emerge with scavengers, insects, small omnivores, and specialized predators. In that setting, under the suffocating heat and reddish skies of the Triassic, the first truly dominant archosaurs appeared. Their bodies were more upright than those of the synapsids. Their legs were positioned directly under their bodies, which gave them a more efficient posture for running. Their lungs were more advanced. Their hearts had better separated chambers, and their bodies were more active. All this allowed them to cover long distances, chase prey for longer, and better withstand extreme conditions. Evolution was beginning to favor speed, endurance, and the conquest of both land and air. From this group, not long after, the first pterosaurs would appear, gliding over Triassic rivers. The Middle Triassic marked the definitive rebirth of life. A planet that had been on the brink of death was slowly, gradually recovering. Ecosystems were no longer fragile skeletons. They were beginning to resemble truly mature communities with forests, plains, swamps, and coasts full of very different organisms. The late Triassic was a time of great contrasts. On the one hand, life had become very diverse and complex. On the other, Earth was getting ready for another disaster. Continents were shifting, volcanoes were erupting, and the climate was starting to become unstable. Something enormous was building up beneath the planet's surface. As Pangaea began to break apart, large rifts opened in Earth's crust and magma rose from the depths. This breakup of the supercontinent not only changed the shape of the land masses, it also altered the global climate and triggered a series of gigantic eruptions that released huge amounts of carbon dioxide. This was the start of one of the largest volcanic episodes in history. The Central Atlantic Magmatic Province, a colossal wound in Earth's crust that, just as had happened at the end of the Permian, would once again put life's ability to endure and reinvent itself to the test. For hundreds of thousands of years, lava flows covered millions of square kilometers, forming regions that today are part of West Africa, Brazil, North America, and Europe. They were true seas of molten rock that, once solidified, created enormous basalt plateaus. Global temperatures rose sharply. The oceans warmed, oxygen levels dropped, and many species could not adapt. Seasons became more extreme, rains more irregular, and ecosystems were subjected to constant stress. Once again, life had to pay the price for these planetary changes. On land, many large archosaurs and giant amphibians almost completely disappeared. In the sea, conodonts, ammonoids, and many marine reptiles died as a result of changes in water chemistry. It was the second major mass extinction in less than 200 million years. Although it was not as devastating as the one at the end of the Permian, its impact was very deep, and it changed the course of life's history. Each of these crises acted like a filter. Some forms disappeared, others were left free to expand. In the midst of all that destruction, there was one group that managed to survive and triumph: the dinosaurs. Their highly active bodies, efficient lungs, and upright posture helped them withstand the extreme changes of the late Triassic. Many of them probably had relatively high metabolisms and grew quickly, which gave them an advantage in an unstable world. While many other species disappeared, the dinosaurs slowly spread, taking over every open niche on the planet. In just a few million years, dinosaurs went from being secondary players to becoming the rulers of life on land. In this era, the first true giants appeared. Among them were the primitive sauropods, ancestors of colossi like Brachiosaurus and Diplodocus. They moved in herds, fed from the highest parts of trees, and were the first land animals to reach weights of tens of tons. Their success was due to a very well-adapted body. Lungs with air sacs, hollow bones, and a slow but very efficient digestion that allowed them to process huge amounts of low-nutrient plants. At the same time, among the predators, the first large theropods emerged, such as Coelophysis and Liliensternus. They were fast hunters that used their speed and jaws full of serrated teeth to bring down their prey. They hunted on open plains and in sparse forests, taking advantage of their agility and sharp vision. In them, we can already see the traits that millions of years later would characterize famous carnivores like Allosaurus and Tyrannosaurus rex. The Triassic was also the time when the first true mammals appeared, descendants of the small cynodonts that had survived the Permian. They were tiny, nocturnal, furry animals with good hearing and mammary glands. They fed on insects, small invertebrates, and perhaps seeds. They lived hidden under the rule of the great reptiles, but that discreet lifestyle would, in the future, be their greatest advantage. When the dinosaurs disappeared, they would already be prepared to occupy the empty niches left behind. In the sky, pterosaurs became more and more varied. Some, like Eudomorphodon, hunted insects with incredible precision, using their pointed teeth like a kind of comb to catch small prey in midair. Others, like Patinosaurus, glided over coastal forests, using warm air currents to save energy. Their wings were not like those of birds, made of feathers, but of a membrane of skin and muscle supported by an enormously elongated finger. They were the first great masters of the air, long before birds existed, and they opened a completely new evolutionary path, that of vertebrates capable of active flight. As the Triassic approached its end, Earth became a world full of contrasts. Huge deserts in the interiors of the continents, warm, shallow seas, and expanding tropical forests. Ecosystems were more complex than ever, but also very fragile. Any volcanic eruption or climate shift could easily upset the balance between species. It was a vibrant planet, but living on the edge. Then, about 201 million years ago, the Triassic ended with another mass extinction. The oceans once again lost their oxygen. The sky darkened with volcanic ash and terrestrial ecosystems collapsed. But this time, the dinosaurs not only survived, they took the place of many animals that had disappeared. What was a catastrophe for other groups became an opportunity for them. When Earth recovered from that chaos, a new era began, the Jurassic. The continents were already starting to separate. The Atlantic Ocean was being born, and the dinosaurs had become the almost absolute rulers of the planet. Around them, pterosaurs dominated the skies, and the first mammals hid in the darkness, waiting for their moment. The Triassic world, with its strange, hybrid, and experimental creatures, had vanished. But without it, the reign of the dinosaurs would never have been possible. The Triassic was like a laboratory in which nature tested new forms of life, a time when Earth reinvented itself from the ashes. And although many of its animals may seem like fantasy to us today, they were real. They walked under the same sun we see, and each of them was another step in the story of how life learned to survive, over and over again. The Triassic was a time of biological experiments like never before. At no other point did evolution dare to try such bizarre things. Every animal seemed like a new idea, a trial by nature to see what worked and what didn't. Many of those strange forms died out without leaving descendants. But the mere fact that they existed shows us that life does not follow a straight path. It is a constant mix of chaos and adaptation. Sometimes the weirdest ideas are just failed attempts. Other times, they become the origin of lineages that will last hundreds of millions of years. Among the strangest animals of the Triassic was Tanystropheus, a reptile with an incredibly long neck, 3 times longer than the rest of its body. Its neck vertebrae were so stretched that its skeleton almost looks like a joke. It is thought to have lived near the water and hunted fish, like a kind of reptilian heron, although no one really knows how it managed to keep its balance with such a disproportionate body. Perhaps it spent much of its time partially submerged, using its neck as a flexible spear to surprise its prey. Tanystropheus is a good symbol of the Triassic, a creature that seems impossible but actually existed, reminding us how creative evolution can be when the planet is reinventing itself. Another equally astonishing creature was Shonosaurus, a huge ichthyosaur that could measure more than 15 meters, 50 feet in length. It had a body perfectly adapted to the open ocean and large flippers for fast swimming. Its shape recalled that of a gigantic dolphin, with a long snout and a hydrodynamic body ideal for traveling long distances in the open sea. Its fossils have been found in what is now Nevada, reminding us that at that time, the sea covered places that are now deserts. Where we now see sand and dry mountains, there was once a deep ocean full of marine reptiles, ammonites, and strange fish. The Triassic also produced small but very curious forms, like Longisquama, a reptile with a row of long structures on its back, similar to feathers or elongated scales. For many years, scientists debated whether it could be an ancestor of birds or just an evolutionary experiment that left no descendants. Most likely, those strange feathers helped it display itself, regulate its temperature, or perhaps glide between trees long before true flight appeared. In any case, Longisquama reminds us that feathers, or feather-like structures, did not arise only for flying, but also for display, insulation, and communication. On land, another baffling animal was Ephigia, which we mentioned at the beginning. At first glance, it looked like a running dinosaur with long legs and a bipedal posture, but it actually belonged to the crocodile lineage. Its narrow skull and beak-like jaw made it look like something out of a strange dream. It is a perfect example of convergent evolution. Very different evolutionary lines that, faced with similar problems, arrive at almost identical body solutions. In swamps and coastal areas lived the placodonts, marine reptiles that looked like turtles, although they were not directly related to them. Henotus, one of the best known, had a flat shell and teeth adapted for crushing shells. It looked like a mix between a turtle and a manatee, a design so successful that evolution would reinvent it millions of years later in other animal groups. These shell crushers kept hard-shelled marine invertebrates under control and were a key part of coastal ecosystems. There was also Drepanosaurus, a small reptile that lived in trees and had an enormous claw on the second finger of its hands, probably used to scrape bark and search for insects. Its tail ended in a bony hook that served as an anchor for hanging from branches. No other animal before or since has had such a structure. It was like a combination of a chameleon, an anteater, and something completely new. Drepanosaurus shows that in the Triassic, nature was not just filling empty niches, but exploring almost impossible possibilities, some of which would never be repeated. And when it comes to Triassic oddities, Chaerovipteryx wins the prize. It was a small reptile with membranes extending from its hind legs, forming a sort of upside-down glider. Instead of flying like a bat or a pterosaur, it launched itself from trees with its legs spread, gliding like a living kite. Its aerodynamic design seems illogical, but it worked well enough for its fossils to reach us. It probably climbed trunks, chose a high branch, and let itself fall to travel short distances from tree to tree, taking advantage of any air current. It is one of those animals that seem designed by someone who has never read an aerodynamics manual. And yet, it flew. In the seas, besides the giants, there were strange creatures like Mixosaurus, an intermediate ichthyosaur that mixed primitive and more modern traits, and the first plesiosaurs, which would later become the rulers of the Jurassic oceans. These were times when nearly every coast, bay, and shallow sea had its own set of marine reptiles, each with a different way of swimming, hunting, and surviving. During the Triassic, the first true crocodiles also appeared, though they did not look much like modern ones. Many were terrestrial and very agile, such as Pseudosuchians, a small predator with long legs that hunted insects and lizards. Others, like Pseudosuchians, were giants, over 5 meters long, true titans of the late Triassic. They walked on 2 legs and had curved, blade-like teeth. They were the undisputed kings of the land until dinosaurs displaced them. For a time, these running crocodiles competed directly with the first theropods, and the result of that competition would determine who ruled Mesozoic ecosystems. The first herbivorous dinosaurs were also very striking. One of them was Plateosaurus, one of the earliest true sauropodomorphs. It had a strong body and a long neck that allowed it to reach tree canopies, a great advantage over other herbivores. It could walk on all fours or rear up on its hind legs to reach higher branches, using its hands for support. It lived in large herds, and its footprints, found in Germany and France, show that they moved together, perhaps following seasonal migration routes. Wherever they went, they left pruned forests and churned up soils, as if living bulldozers had passed through. Plateosaurus was one of the first warnings of what was to come, a world dominated by long-necked giants that would transform Jurassic landscapes. The Triassic was a time of great evolutionary creativity, but also of limits. Many of these creatures were destined to disappear. Ecosystems were unstable, volcanoes were still active, and each new form of life had to adapt to a changing, harsh planet. There were prolonged droughts, abrupt temperature changes, and seas that repeatedly altered their chemistry. It was not an ideal world, but an extreme testing ground. Even so, even the species that failed left their mark. Every Triassic animal was an experiment in the history of life, and without those attempts, with their successes and mistakes, the modern world would not be as it is. Many traits we see today in modern animals, more efficient lungs, upright postures, specialized teeth, flight, and gliding strategies, were first tested in that period, sometimes in lineages that did not survive to the present, but that opened the way for others. Deep in the forests, under burning skies and above still warm seas, the path of evolution was being decided by forms of life we can barely imagine today. And among them, one lineage began to stand out from the rest: the dinosaurs. At first, they were just another group, small and inconspicuous, but they had just the right combination of features to thrive on an unstable planet. Active bodies, rapid growth, light skeletons, and very efficient lungs. By the time the Triassic ended, the world had changed completely. Earth had passed through fire, death, and rebirth. From the destruction of the Permian, a new planet had emerged, with more complex ecosystems, tougher organisms, and a lesson engraved in every fossil. Life never gives up. Each layer of Triassic rock tells part of that recovery, like pages of a book written in bones, footprints, and sediments. The Triassic was a bridge between two worlds. It linked the primitive past of reptiles and synapsids with the future dominated by dinosaurs, birds, and mammals. It was the moment when nature dared to try almost every possible combination. Reptiles with impossible necks, gliding creatures before true wings existed, running crocodiles, tiny mammals hidden in the shadows. A huge open laboratory where evolution showed it could reinvent itself even after the greatest catastrophe in history. Without that strange, experimental, and turbulent period, the world as we know it, including us, would never have come into existence. From those strange animals arose the forms that would dominate the next 150 million years. Pterosaurs would conquer the sky, dinosaurs the land, and marine reptiles the oceans. And in the shadows, small nocturnal mammals learned to survive, waiting for the opportunity that would come much later, when the great reptiles disappeared. Throughout that time, they stayed discreet, hidden in burrows, trees, and cracks in the rocks, living at night to avoid giant predators. They seemed like side characters in the story, but they were the silent reserve of the future. The legacy of the Triassic is not only in the fossils we find, but in the very logic of how life works. Every time one species goes extinct and another takes its place, every time an ecosystem collapses and another is born from its remains, the spirit of the Triassic reappears. That was its essence: resilience, the capacity to start again from nothing. It is as if the biosphere had learned, through repeated blows, that change is the only constant, and that the only possible strategy is adapt or disappear. Looking at the Triassic is like looking at ourselves in a very old mirror. We are the descendants of a long chain of survivors that endured fire, drought, hunger, and extinctions. In our DNA, we carry the imprint of those reptiles and of those small cynodonts that struggled to breathe under a blazing sun. They showed for the first time that life could be reborn, even when everything seemed lost. Without their persistence, without their fortunate mutations and survival strategies, there would be no modern forests, no birds, no us. Today, when we see the fossils of Tanystropheus, Henotus, or Ephegia, we are not looking at monsters or meaningless oddities, but at the first drafts of modern life. Every strange form of the Triassic was nature's attempt to find a balance between form and function, between adaptation and something close to beauty. Their bones, trapped in rock for more than 200 million years, are pages of a book we are still learning to read, but that tells a very clear story. That of a planet that refuses to give up. Out of all that initial chaos came the foundations of the modern world. Atmospheric oxygen stabilized, the seas regained their chemical balance, and forests began to cover the continents once again. The dinosaurs inherited the Earth, but the real legacy of the Triassic was deeper. It taught life how to withstand collapse and reinvent itself after every end of the world. Thanks to that lesson, every time we talk today about ecological recovery, resilience, or systems that rise again after a catastrophe, we are, without knowing it, invoking the same principle born in that remote age: life's stubborn determination to carry on. If the history of evolution were a book, the Triassic would be the chapter where the plot breaks and the protagonist has to start from scratch. The tragedy of the Permian had wiped out almost everything, but the Triassic wrote a new beginning. And from that beginning, we all come. It was not just a simple sequel. but almost a different story using the same stage, the same Earth, the same physical laws, but a completely new cast of species, testing biological solutions that had never existed before. Every species you see today, birds, mammals, reptiles, and even us, carries within it an invisible imprint of that period. We are the distant descendants of an Earth that learned how to survive its own hell. In our bones, in the structure of our lungs, in the way our metabolism is organized, there are traces of evolutionary decisions made back then. When a bird flies, a mammal nurses its young, or a reptile basks in the sun to warm up, it is using strategies that were fine-tuned in that burning world of the Triassic. That is how the Triassic ended. Not with a simple ending, but with a promise. The promise that as long as a little life remains, the planet will be able to fill up with living beings again. The promise that chaos is not the end, but the beginning of something new. Thanks to that, the story of the Triassic is still alive. It is under our feet, in every fossil, in every cell, and in every breath. Every time you inhale oxygen, a gas that also went through its own crises and readjustments, you are unknowingly taking part in an unbroken chain that connects that remote world with the present. Because the real miracle was not the appearance of dinosaurs or the evolution of mammals. The real miracle was life itself, rising again and again, refusing to disappear. What is astounding is not just the diversity of forms, but the tenacity, the ability to reorganize after every blow, to try again with new combinations. And that miracle, that force that made life spring from the ashes, still exists today, reminding us that the universe, even in its darkest moments, always finds a way to begin again. As long as there is one organism that endures, one seed that germinates, one mind capable of imagining a different future, the story is not over. We are heirs to that cosmic stubbornness and, at the same time, responsible for what we write in the coming chapters.